Hello students, welcome to Talk on Civil Engineering. Let us discuss a problem on one-way slab design. So here you have a question to design a one-way slab having a clear span of 3.6 meters, 3.6 meters, and it is supported on a wall, a masonry wall of 230 mm, and is carrying a live load of 3 kilonewton per meter square, and surface finishing we have to consider as 1 kilonewton per meter square, and steel grade is 415 and M20 concrete. Okay, let us solve this. Let us design this one-way slab. Okay, so usually we'll for one-way slabs we'll be designing the one-way slab with respect to the shorter span. Okay, so that's the reason he has provided only one direction. So only the shorter span he has provided. So this is 3.6 meters. So you no need to you no need to have this longer span. So longer span to manaku avasaram ledu, only shorter span unte chalu. Okay, and even you no need to determine whether this is one way slab and two way slab, because in the question itself he has mentioned that it is one way slab, right? Now the first step, we need to determine the effective depth. So calculation of effective depth D. Okay, so in order to find out the effective depth, we need to assume the L by D ratio. So you can assume L by D ratio between 25 to 30. You can assume between 25 to 30, or else you can assume 40 mm thickness, 40 mm thickness for every 1 meter span. Okay, so these are the two cases you can consider to find out the effective depth or overall depth of the section. Okay, so it just is ఒక assumption లాగానే తీసుకుంటాం. After that we'll check whether this provided effective depth is sufficient or not with respect to the bending moment, right? Now let us consider the L by D ratio around, let me consider the L by D ratio as 28. So this L by D ratio also, for a shorter span you have to consider higher value. For a lesser ratio, I mean for a longer span you have to consider the lesser ratio. Okay, so more the span, so less will be the ratio. Okay, or more will be, more the lesser the span, you have to consider more ratio. Okay, so that's the reason I'm considering 28, because my span is only 3.6 meters, so 28 is enough. So my span is 3.6 meters. So let me write this in terms of mm. So 3600 mm divided by 28. So then my D will be 3600 divided by 28. So it will be 128.57. So it is 128.57. So I can consider as I can consider 130 mm as my effective depth. Okay, so in other way you can take this 40 mm thickness for every 1 meter. This is also one of the thumb rule to fix the total depth. So 40 meters, 40 mm means 40 into, so how many, what is the span? 3.6. okay, so 40 into 3.6 will comes around 144. 144 means you can fix 150 mm has the overall depth. This is nothing but is overall depth. So from this you have to fix the effective depth by taking effective cover. Okay, so this both the ways you can fix the effective depth and overall depth of the section, right? So now let us go through this L by D ratio itself. So here L by D ratio, through L by D ratio we got the effective depth has 130 mm. Okay, and let us take the overall depth as 130 plus, let me consider the effective the effective cover has 30 mm. So usually for a slab nominal cover will be Nominal cover will be 20. So for this, you can add around half of the dia of the bar. So like 12 or 20 is okay. So I'm adding 10 mm. Okay. So I'm considering effective cover as 30 mm. So it will be 160 mm. So my overall depth is 160 mm. Okay. Now, after fixing this depth of your slab, the next step is to calculate the effective span. Effective span calculations. So in this, you are having two cases, that is the clear span plus effective depth, and the second one is clear span plus half of your support on either sides. Okay. So clear span is 3.6 meters plus your effective depth is 130, right? So it is 0.13. So it will be 3.6 plus 0.13. So it will be 3.73. 3.73 meters. And here it is 3.6 plus what is the support width? 230 is your support width. So it will be 0.3 by 2 plus 0.23 by 2. So it will be 3.6 plus 0.23. So it will be 3.83. So from this, the least value will be your effective span. So the least value is 3.73. This is my effective span. Okay. So I got my effective span. The next condition is you need to calculate all the required loads. So load calculation is my third step. Load calculation. So here this I will calculate the factored load. Okay. Right. So the first one is the dead load. So for calculating the dead load, so we will be considering the 1 meter width. So the slab is nothing for designing of slab is nothing but it's like a rectangular beam. Slab అనేది beam లాగానే ఒక rectangular beam లాగానే మనం డిజైన్ చేస్తాం, having depth and width of 1 meter width. So 1 meter width and having a depth d. So it looks like a rectangular beam. So we'll consider it is as a rectangular beam and we'll design. That's it. So width b and depth into the unit weight for a RCC, it is 25. Okay. So what is the width? Width is 1 meter. And what is the depth? Depth is 160 mm. So it is 0.16 into 25. So it will be 0.16 into 25. So it is 4 kilonewton per meter. Okay. Now let us find the live loads. So live load he has mentioned in the question itself. He has provided live load as 3 kilonewton per meter square. So for this you can multiply unit meter, that is 1 meter, it will comes to 3 kilonewton per meter. Okay. Similarly, so floor finishing he has mentioned as 1 kilonewton per meter square. So for this we have, let us multiply unit meter. So it will comes to 1 kilonewton per meter. So what is the total load? So total load is 4 plus 3, 7, 7 plus 1 is 8. So 8 kilonewton per meter is a total load, total W. And what is the factored load? Factored W is equal to 1.5 into 8. So it is 12. So 1.5 into 8. So it is 12 kilonewton per meter. Okay. So we got the factored loads. Now the next step is to find out the factored moment. Factored moment or bending moment. So we know it. Let us consider this is as a UDL acting on the simply supported beam. So the formula will be bending moment formula. It is WU LE square by 8, right? So WU is 12 and LE is, it is 3 point, how much we got? 3.73, right? So 3.73 square divided by 8. So it is 12 into 3.73 square divided by 8. So it is 20.86. 20.869. So let us take 20.87 kilonewton meter. Okay. So this is the bending moment, factor bending moment that we are getting. So let us equate this with mu limit so that we can check whether the provided effective depth is safe or not. Okay. So let us equate this bending moment with mu limit. So for Fe 415, the mu limit formula is 0.138 FCK BD square. Okay. So here your bending moment is 20.87 into 10 to the power of 6 is equal to 0.138 into FCK is 20 and B is 1000 and D you need to find out D square. Okay. So D will be under root 20.87 into 10 to the power of 6 divided by 0.138 into 20 into 1000. Okay. So your D will be 20.87 into 10 to the power of 6, 0.138 into 20 into 1000. Yeah, so it is 86.95. So the provided is much greater than this one. How much we have provided? D, that is 130, right? So 130 mm we have provided, which is greater than the required value. So therefore, it is safe. Okay. Now the next step is you need to find out the reinforcement required. So what is the step number? Yeah, 5. So step number 5, calculation of reinforcement. The main reinforcement. This is the main reinforcement which is provided along the shorter span. Okay. So to find out the AST required, you can use this 0.5 FCK Fy 1 minus under root 1 minus 4.6 mu divided by FCK BD square B into D. So you can use this formula, or else you can use another formula which is provided in IS 456 with respect to mu. So mu is equal to 0.87 Fy ASTD 1 minus Fy into AST divided by FCK BD. So you can use this equation also to find out the AST. Okay. So let us substitute all the values here and find out what is the AST that you're getting. So I have used this formula. So you can use any formula. So I'm using, if you use this formula, you'll get a clear-cut answer. Whereas if you use this formula, you'll get 2 answers. Okay. So here I got the answer as the area of steel has 481.9 mm square. So after this, you need to find out the spacing of the bars. To find out the spacing of the bars, so you need to divide small AST divided by capital AST, which is distributed in unit meter 1000. Okay. So I'm assuming a dia of 12 mm. So if I assume a 12 mm dia, so the area will be 512 square by 4 divided by how much AST I got? It is 180.9. So which is distributed in 1000. So it will be 481.9 into 1000. So we are getting around 234.6. So we can provide 230 mm center to center. Okay. So that is the spacing we got. Now we have calculated the main reinforcement. Now we need to calculate the distribution reinforcement. Let us calculate distribution reinforcement. Before that, you can check for spacing also. This spacing that you have provided, it should not be greater than, the spacing should not be greater than 3 times of d or 300 mm. Okay, so 3 times of d will be 3 into 160, so it will be more than 230. 3 into 130, so it will be 390 mm. So the least one is 230 only, so that's the reason we are providing 230. So therefore, has a main reinforcement provide 12 mm dia bars at 230 mm center to center along the short span. Okay, so now coming to the distribution reinforcement, the sixth step, distribution reinforcement. And we know that distribution reinforcement is nothing but your minimum AST, right? So AST minimum. So for a slab, the minimum AST, if you are using HYSD bars, it is 12% of B into D. Okay, so 12% means it's 0.12 divided by 100 into 1000 into 160. So it will be 0.12 into 100 into 1000 into 160. So it is 192 mm square. So let us provide 8 mm dia bars. 8 mm dia bars. So if you provide 8 mm dia bars, so what will be the spacing? The spacing will be same AST minimum divided by AST minimum into 1000. So it will be 5 by 4 into 8 square. 8 square divided by 192 into 1000. So we are getting a spacing of around 261.7. So we can provide 260 mm center to center, and the check for spacing is 5 times of D. So 5 times of D will be 5 into 130. So it will be 650 mm or 450 mm. The least value is 260 mm is the least. So we have to provide 260. So therefore, has a distribution bars provide 8 mm dia at the rate of 260 mm center to center along longer span. Okay, so with that, we have calculated all the required data, reinforcement on along shorter span and longer span, and you can draw the relevant diagram to this. So if this is your slab, so along shorter span you have to provide main reinforcement, something like this. So this is my reinforcement, and along the longer span you have to provide the distribution reinforcement. So this is your 8 mm dia at 260 center to center, and about this it is 12 mm dia at 230 center to center. Okay, and even you can draw the cross section profile also. So you can, I hope you can do that on your own. And the one more thing is left, that is you have to check for the deflection. You have to check for the shear also, but mostly slab will be safe against shear. So that's the reason sometimes you can skip that, but check for deflection is very important. So let us check for the deflection control. Okay, So for deflection control, we know that LD max. So the L by D provided should be less than or equal to the maximum or limiting L by D ratio. Okay, so what is this L by D max value? So it is L by D basic value that is provided in IS 456 into KT into KC. So this KC is the compression coefficient for compression reinforcement. Since there is no compression reinforcement for the slab, so you can take this value as 1. Okay, and what is this KT? So KT is nothing but you'll get this from figure 4 from IS 456. Just look at that figure 4. So in that you need to calculate the FS value, stress in steel value, stress in steel, and the percentage of steel that you have provided. So corresponding this, you will get the KT value. And what is L by D basic value? So L by D basic value is provided with respect to the support condition. So for a simply supported slab, the L by D ratio is 20. So you can take this since it is a simply supported slab, so the basic value you can take as 20. Okay, so by substituting all these values, so if the L by D that is provided, so here L by D, L is 3.6 and D is 130. So 3600. So what is L by D value you are getting? So it is 3600 divided by 130. So you are getting around 27.69. If this is less than or equal to L by D maximum value, then you can say it is safe. It is safe. It is safe against deflection. Okay. So that's it, ma. So I hope you can calculate this KT. Just look at figure 4 and you can easily calculate what is KT, right? So this is how we'll design the one-way slab, right? So later we'll see how we can calculate the two-way slab also in next video lecture. Thank you all.